These men are maintenance mechanics. Like you, they're responsible for keeping many different kinds of equipment in top running condition. A lot of the equipment they work on is pumps, which are connected to a motor or other prime mover. Without the motor, the pump is useless. In many ways, the connection between the pump and the motor is as important as the pump and the motor themselves. This is the device that connects the motor shaft to the pump shaft. It's called a coupling, and couplings are what we're going to be talking about today. As we'll see, couplings, like the equipment they connect, have to be kept in good working condition. They also have to be properly lined up. When a coupling and two shafts are lined up like this in a straight line, they are properly lined up. The term for this is alignment, and proper alignment between couplings and shafts is what we're after. Whenever two shafts are not perfectly lined up, they are misaligned. The further out of line they get, the worse the misalignment. And a misaligned system doesn't work very well, if it works at all. Misalignment is the biggest coupling maintenance problem you're likely to run into. So, it's important for you to learn how to detect and correct it. By learning how to deal with alignment problems now, your job will be a lot easier later on. To start this session, we're going to take a close look at shaft couplings like this one. We'll learn their purpose, and we'll see two major types: grid-type couplings and gear-type couplings. And we'll examine the parts of each type. Then we'll go step by step through the process of disassembling a grid-type coupling. Later on, we'll see how to correct shaft misalignment. Let's start by seeing how couplings are used. Couplings serve three purposes. They connect two shafts, they allow the shafts to be separated, and they adjust for slight misalignment. The first purpose is to connect two shafts. This allows power to be transmitted from the motor to the pump. In case you're wondering if a single shaft between the motor and the pump could accomplish the same thing, well, it could. But with a single shaft, you run into some serious problems. For example, when doing a pump overhaul, you'd have a difficult time trying to separate the pump from the motor. Using a coupling between two shafts solves this problem. As a matter of fact, the second purpose of couplings is to enable you to separate the two shafts so that the coupling or the units that it connects can be easily worked on. Another problem with a single shaft is that over a period of time, motors and pumps have a tendency to shift slightly. A single shaft can adjust to this misalignment and may break. Couplings solve this problem by providing system flexibility. When equipment shifts, the coupling can adjust slightly and spare the shaft from serious damage. Basically then, there are three purposes of shaft couplings: to connect two shafts, to allow you to separate the shafts when necessary, and to adjust for slight misalignment. Okay. Now let's take a closer look at some couplings. We'll start with a grid type because you'll frequently come in contact with it, especially in smaller pumps. What you see here is a grid type coupling separated into its various parts: the grid, which gives the coupling its name, the hubs, the cover gaskets, the seal rings, and the nuts and bolts needed to hold these parts in place. If we were to take these parts and put them all together, we would see that the hubs fit close together and that the grid meshes into the coupling teeth to connect the hubs. The cover halves then bolt together to form a casing around the hubs. A fully assembled grid-type coupling looks like this. We're going to use this coupling to demonstrate routine maintenance procedures: disassembly, cleaning, inspection, and reassembly of the coupling. Before we begin, we consult the manufacturer's instruction manual for the specifications of the coupling and any special instructions. This is done before starting any coupling maintenance job. And we also review all plant procedures and safety precautions that apply to coupling maintenance. Finally, we tag out the equipment we'll be working on by following the plant's tagging procedures. For this demonstration, we brought this pump and motor into the shop where there's plenty of room to work. Usually, though, you'll find yourself working on pumps like these, where there's very little room to move around. Here in the shop, ventilation is no problem. But no matter where you do the overhaul, always be sure that your work area is properly ventilated. Even fumes from non-toxic solvents are no substitute for air. Once you're prepared to do the job correctly and safely, make sure that any parts you need are available. Next, you want to make sure you have all the tools you need. You're now ready to disassemble the coupling. Normally, an equipment guard covers the coupling to protect you from the rotating parts. Remove this guard and inspect the inside of it. Look for signs of grease that may have been flung out of the coupling while the equipment was running. Next, lay a pan directly under the coupling. Use the pan to set the parts in as you remove them. Then, wipe excess grease and dirt off the cover and the shafts with a clean rag. This is important because it prevents grit on the outside of the coupling from getting into the internal parts when you remove the cover. To be certain you put the cover halves back in the same position later, use a center punch or other pointed tool to make witness marks on both halves. By matching these marks during reassembly, you'll be sure that the cover is properly lined up. Next, the bolts that hold the cover halves together are loosened and removed. Then the halves are separated from the hub one at a time. Be sure to remove the cover carefully so as not to damage the seals inside. Set both halves in the pan, and remember to remove the gaskets and set them aside. With the internal parts exposed, you can slide the seals off the hubs and out of the way. Then use a rag once again to wipe excess grease off the hubs and the grid. This will enable you to locate the open ends of the grid more easily. Rotate the coupling until you find the open ends of the grid. That is, the point where the two ends of the grid are joined. Using a screwdriver, pry one end loose from the hub teeth. Lift it far enough so that you can get a hold of it with your hand. But don't bend it back or attempt to peel it off the hubs. Instead, wiggle the grid back and forth to free it, being careful not to bend it or twist it out of shape. Once the grid is free, slide it onto the shaft, where you can remove it without having to open it too far. With the coupling completely taken apart, you're now ready to clean all parts thoroughly. Start with the hubs. Using a clean rag, remove as much remaining dirt and grease as possible. Then do the same for both cover halves. Be certain to clean all ridges and small corners, as well as smooth, flat surfaces. As long as the pan is under the coupling, solvent can be poured directly over the hubs, and a soft bristle brush can be used to give all hub surfaces a thorough cleaning. Using the brush and the solvent that collects in the pan, clean the grid. Then use a rag dipped in solvent to clean grease and dirt off the seals. Finally, set aside all clean parts and cover them with a rag until it's time to put them back together. This completes the procedure for disassembling and cleaning a grid-type coupling. There's a second common type of coupling you also need to know about, the gear-type coupling. To get an idea of the differences and similarities between grid-type and gear-type couplings, take a close look at this exploded view of a gear-type coupling. Notice that gear-type couplings have hubs, just as grid-type couplings do. They also have seals to keep the lubricant inside the coupling. Except for the retaining rings at either end, the major difference between a grid-type coupling and a gear-type coupling is that the gear type has a sleeve instead of a grid. In a grid-type coupling, like this, power is transmitted from the motor shaft to the pump shaft by a grid connecting the teeth of both hubs. In a gear-type coupling, a sleeve engages the teeth of both hubs. These two types of couplings illustrate the one basic principle by which most mechanical couplings operate. The shafts are attached to hubs, and the hubs are connected by a third part, such as a grid or a sleeve, that transmits the power from one hub to the other. This arrangement also allows you to separate the shafts when necessary and enables the system to adjust to slight misalignment. There are other types of couplings that are less common than grid and gear types. These include jaw, hydraulic, magnetic, and disc-type couplings. And there are variations even among grid-type couplings. In some, the covers open vertically. In others, like the one we saw disassembled and cleaned, the cover opens horizontally. If you understand how grid and gear-type couplings work, you'll have a good foundation for doing maintenance on most couplings you'll have to deal with. Before you begin work on any coupling, though, remember to consult the manufacturer's instruction manual. It's the best source for detailed information you need to do the job. In a minute, we'll come back and inspect the parts of this coupling for damage. But first, stop the tape and review the material we've covered so far. So far, we've looked at the purpose of couplings and the major components of grid and gear types. We also started an overhaul by taking apart and cleaning a grid-type coupling. The next step in an overhaul is to inspect the individual parts. In this segment, we'll see what to do and what to look for when inspecting a coupling. Next, if we find that all of the parts of this coupling are in good working order, we'll put the unit back together. Finally, we'll spend a few minutes talking about how to replace a hub that's worn or damaged. This grid-type coupling has been disassembled and cleaned, so it's ready to be inspected. Now, what exactly do you look for when inspecting a coupling? Well, for the most part, you look for signs of wear or damage. Now, this grid isn't from the coupling we're working on, but it does serve to give us some common indications of wear. Notice these flat, shiny spots. They were caused by misalignment. Also, this grid is broken. If the grid from the coupling we're working on looked like this, it would have to be replaced. The hubs must also be inspected. Make sure that the teeth are in good condition, that none of them are cracked, chipped, or excessively worn, like these. Be sure to check the seals, too. Remember that the seals must be in good condition if the internal parts are to stay properly lubricated during operation. Rotate each seal around the shaft, feeling for dents, flat spots, or cracks through which lubricant could leak out of the coupling. Then try wiggling the hubs to make sure that they fit tightly. If either hub doesn't fit properly, it will probably have to be replaced. Remember that we began this job as a routine maintenance task. We were to disassemble the coupling, clean it, inspect it, and reassemble it. So far, we've disassembled and cleaned it, and we've inspected for damage and wear. Before reassembling the coupling, however, we have to inspect for one more thing: proper alignment. Up to this point, we haven't said much about alignment, and we'll be covering it in detail later. But as a part of any routine inspection, you should at least make a rough check of the alignment of the hubs. When checking alignment, you're checking the position of one hub in relation to the other. Both hubs should be on the same level horizontally and vertically. Also, the space between the hubs should be the same at all points and within the specifications listed in the manufacturer's instruction manual. Although we'll be seeing more accurate ways of measuring alignment, you can make a rough alignment inspection using a scale and a feeler gauge or a wedge gauge. Simply lay the scale across the top of both hubs. If the alignment is correct, the scale will lie perfectly flat. Repeat this procedure along the sides and at the bottom of the hubs. To make sure the distance between the hubs is the same all the way around, measure the gap with a wedge gauge or a feeler gauge, as the mechanic is doing here. Insert the gauge at the same 4 points where you measured with the scale. At the top, the bottom, and at both sides. If the gap between the hubs measures the same at all 4 points as it does here, the alignment is correct. This rough alignment check completes our inspection. Since all the parts of the coupling are in good shape, we're ready to start the reassembly procedure. Now, reassembly means two things: putting all the parts together according to specifications and properly lubricating the parts to make sure they work smoothly. Because lubrication is so important, the first step in reassembly is to check the manufacturer's instruction manual for the type of lubricant recommended for the equipment. To do the job right, use only the type of lubricant listed in the manual. Using your hand, pack lubricant into the spaces between and around the hub teeth. Make sure all critical surfaces are thoroughly coated. By critical surfaces, we mean any place where the grid touches the hubs. It's at these points that the grid and the hub teeth will wear first, if not properly lubricated. In addition, it's important to force as much lubricant as possible between the hub faces. This further ensures adequate lubrication. When all critical surfaces have been well coated with grease, install the grid. To avoid having to open the grid too far and risk damaging it, slip it over the shaft first. Slide it carefully over the hub teeth. Then, beginning at one end of the grid, press the loops one at a time between the teeth. Work slowly and carefully. Be sure that each loop meshes correctly into place. Grid. Again, remember that adequate lubrication is important and that without it, the internal parts could wear very quickly. Next, position the seals on the hubs. The seals should not be placed up against the grid and the hub teeth. Instead, they should be located far enough from the grid to fit properly into the cover halves. Now you're ready to install the cover halves. Start by greasing the flanges of the lower cover half. This grease will hold the gaskets in position while you're installing the cover around the hubs. Then, lay the gaskets on the greased flanges. In most cases, it's best to use new gaskets each time you overhaul a coupling. If the old gaskets are in good shape, however, this may not be necessary. Once the gaskets are in place, fit the lower cover half into position on the bottom of the hubs. Be particularly careful not to pinch or damage the seals when installing the cover. Both seals should fit comfortably into the grooves on the inside surface of the cover. Hold the lower half in place while fitting the upper half over the hubs. Again, it's important to be sure the seals fit properly into the grooves on the inside of the cover. Carefully press the upper and lower halves together. Don't worry about any excess grease that squeezes out. But do make sure that the gaskets are properly lined up before trying to bolt the cover halves together. Then, insert the cover bolts through the flanges one at a time and attach a nut to the end of each bolt. Some manufacturers recommend that the cover bolts be tightened with a specific amount of force or torque. If this is the case, you'll have to use a torque wrench to tighten the bolts. You'll also have to check the manufacturer's instruction manual to find out how much torque is required. When the bolts are tightened properly, use a clean rag to wipe excess grease off the surface of the coupling and the shafts. Then, adjust the cover by sliding it sideways until it's in position over the center of the hubs. Finish the job by replacing the equipment guard that protects you from the rotating parts. Then, have the operator line up the equipment so that it can be tested and put back into service. A satisfactory operational test is the final step. This completes the reassembly procedure. Luckily, we found all the parts of this coupling in good order. That made our maintenance job a lot easier. But in some cases, a hub needs to be replaced. As a matter of fact, there are two situations that require hub replacement. First, replace a hub when it shows signs of wear or damage. And second, anytime you replace a pump or a motor, put a new hub on the shaft. When you replace a damaged hub or mount a hub on the shaft of a new pump or motor, you have two choices. You can take an old hub in good condition and put it on the shaft, or you can mount a new one. In either case, the procedure is basically the same. To give you an idea of what has to be done to replace a hub, we're going to spend the next few minutes talking about the major steps involved. Let's assume that when you took this coupling apart and gave it a good cleaning, you found that the hub had to be replaced. First, look in the manufacturer's instruction manual to find out what size hub you need to replace the old one. Then, order the new hub. As soon as you receive the new part, you can begin reassembly. Give yourself enough room to work by unbolting the motor from its bed plate and swiveling it to the side. If the hub is fastened to the shaft with a set screw, check to see what kind of a screw it is. Then use the appropriate tool, in this case an Allen wrench, to loosen and remove it. In most cases, the old hub will fit too tightly to the shaft for you to pull it off by hand. This means that you'll have to clean the end of the hub and the shaft and use a gear puller to press off the old hub. When you use a gear puller, use a center finder with it. The center finder saves wear and tear on the gear puller. It also helps you to line up the gear puller and the shaft properly. The shaft, center finder, and spindle of the gear puller should be lined up in a straight line. This ensures that the hub is pulled off evenly without damaging the shaft. You'll probably find that it will take some juggling to get everything squarely into place. When the gear puller is securely in position, attach a wrench to the end of the spindle and begin pressing off the hub. The hub will eventually slide off the end of the shaft. When it does, remove it from the gear puller and set everything aside. Be particularly careful not to misplace the center finder. Next, remove the key from the keyway and put it where it won't get lost. Inspect the shaft very carefully. Feel for ridges, burrs, and rough spots. Clean all old grease out of the keyway and off the shaft. Look for cracks and other damage that could later lead to shaft failure. If necessary, use a crocus cloth to polish the shaft so that you can inspect it more easily. The idea is to get the shaft as clean as possible so that you can check it to be sure it doesn't need to be replaced. The next step is to measure both the shaft and the new hub to be sure they'll fit together properly. The manufacturer's instruction manual lists the maximum difference allowed between the outside diameter of the shaft and the inside diameter of the hub. Locate this information in the manual and write it down. Then, use an outside micrometer to measure the diameter of the shaft. Be certain to attach the micrometer so that it measures the full diameter. Read the measurement to the nearest thousandth of an inch and write it down. Next, measure the inside diameter of the hub. You can use either an inside micrometer or a telescoping gauge, like the one the mechanic is using here. Either way, be sure your measurement is accurate to the nearest thousandth of an inch. Again, write down the measurement. Now at this point, you want to know if the difference between the outside diameter of the shaft and the inside diameter of the hub is within specifications. To do this, subtract the diameter of the shaft from the diameter of the hub, and check your answer against the specification you found in the manual. Because the hub is designed to fit tightly on the shaft, you may have to heat it to get it on. Heating expands the hub and increases its inside diameter. When the hub has been adequately heated, lubricate the shaft and the keyway according to the manufacturer's instructions. Then, set the key in place, being sure its end is flush with the end of the shaft. Using asbestos gloves or other heat protection, slide the new hub onto the shaft. If you're having difficulty, use a soft-faced hammer to tap it gently into place. The face of the hub should be almost flush with the end of the shaft. Insert the set screw and tighten it. This will lock the hub in place. Then, use a clean rag to clean excess grease off the shaft and the hub. Next, mount a dial indicator so that its stem touches the hub, and use the dial indicator to take a run-out reading. A run-out reading is designed to find out whether or not the hub is perfectly round. Start by setting the dial indicator to 0. Then, slowly rotate the new hub one full turn. As long as the indicator continues to read 0, you can be sure the hub is round. If the needle moves from 0, however, notify the lead man on the job. The new hub is not round and should be replaced. With the hub replaced and checked for roundness, all you have to do is reassemble the coupling using the procedure we saw before. We've covered a lot of material in this segment. We saw how to perform a coupling inspection. We covered the major steps in cleaning and reassembling a coupling. Finally, we saw the procedure for replacing a worn or damaged hub. But there are two things in particular I want to stress. First, do everything you can to keep dirt out of the coupling. Second, make sure the coupling is properly greased. After a short break, we'll talk about the principles of shaft alignment. In the preceding segments, we saw two types of couplings and performed routine maintenance on a grid-type coupling. One word that kept coming up was alignment. Alignment, as you remember, refers to the proper positioning of the shafts and the coupling. We already saw the procedure for doing a rough alignment check with a scale and a wedge gauge. In this segment, we're going to talk about alignment in more detail. We'll see how to measure and correct misalignment. We'll talk about different types of misalignment that can occur between two shafts, and we'll examine the tools and parts you need to do an alignment job properly. Most of the time, no one is going to tell you if shafts are misaligned. You have to find this out for yourself. If the equipment is running, there are three clues you can look for: excessive vibration, high bearing temperature, and unusual noise. Check for vibration with a vibration meter. Try doing this to several pumps around the plant to get an idea of what normal vibration feels like. Next, check bearing temperatures with a thermometer or with your hand. Finally, listen for unusual noises. If the coupling is noisy, again, misalignment could be the problem. Remember, though, that excessive vibration, high temperature, and noise are not always obvious. Only if you make it a habit to check the equipment regularly will you get a feel for what's normal for that equipment and be able to detect abnormalities when they occur. Of course, you can't detect these symptoms when the equipment isn't running. But there is one symptom of misalignment you can check for when the equipment is down for maintenance, and that's uneven bearing wear. On this sleeve bearing, one end is worn more than the other. The grooves on this end of the bearing are an example of wear caused by misalignment. By comparison, this bearing shows no uneven wear. During routine maintenance, you won't be taking the unit apart to inspect the bearings, but you can test for bearing wear by rotating the shaft and feeling for drag or unsmooth motion. Try wiggling the shaft too, to be sure there isn't any looseness that could mean worn bearings. Even if you can't find any sign of bearing wear, you should still measure for possible misalignment, just like we did during the coupling inspection. Before we go into detailed measuring procedures, let's make sure we know what we're measuring. There are two types of misalignment: parallel misalignment and angular misalignment. Parallel misalignment occurs when one shaft is higher than the other, or when one shaft moves to one side of the other. When one shaft is offset to the side, that's horizontal parallel misalignment. When one shaft is offset higher than the other, like it is here, that's vertical parallel misalignment. In both cases, the center lines of the shafts are parallel to one another. The difference is that one center line is offset from the other. They're either like this or like this. With angular misalignment, the shafts meet at an angle. They are at either a horizontal angle, giving us horizontal angular misalignment, or at a vertical angle, giving us vertical angular misalignment. Even though we've shown parallel and angular misalignment separately, you'll find through experience that improper alignment is usually a combination of both. As a result, we often end up with an arrangement like this, where the shafts are slightly offset and at a slight angle to one another. Correcting shaft misalignment begins with measuring to find out how much the system is out of line. There are 4 tools used to take these measurements: a scale, a wedge gauge, a feeler gauge, and dial indicators. Your goal in coupling alignment should be the closest alignment possible. But no matter how accurate you are, hooking up suction and discharge piping after you've finished might put enough stress on the equipment to throw the shafts out of alignment again. To keep this from happening, be sure all piping is installed before you start your alignment. You should also know that some equipment requires a vertical difference between the coupling halves. This vertical difference may be necessary in equipment that heats up when it runs. As the equipment warms up, it expands, moving the shaft and one hub of the coupling. When the equipment stops running, it cools, and the hub returns to its original position. As you can see, a vertical difference allows for these changes by making sure that the hubs line up during normal operations, when alignment really counts. So, check the manufacturer's instruction manual to see if any vertical difference between coupling halves is specified. For this pump, none is necessary. If you look at this coupling, it isn't easy to see any misalignment. The only accurate way to check for misalignment is to measure it. Always measure for angular misalignment first. When checking for angular misalignment, you might find it helpful to think of the end of the motor hub as though it were the face of a clock. Consider the top point as 12 o'clock and the point directly below is 6 o'clock. On each side, of course, are 3 o'clock and 9 o'clock. Keeping this in mind, all you have to do to check for angular misalignment is to insert a wedge gauge at all 4 points around the hubs. Begin at the 12 o'clock position and be sure to write down each measurement as you take it. Repeat this procedure at the bottom of the hubs, that is at the 6 o'clock position. Again, write your measurement down before going on to measure at 3 o'clock and 9 o'clock. Let's assume these shafts are misaligned. How do you correct angular misalignment? Well, if the angular misalignment is horizontal, it has to be corrected by loosening the foot bolts and sliding the motor sideways until the alignment is correct. If there is vertical angular misalignment, use shims. Shims are pieces of steel or brass like these. They're placed in pairs under the feet of equipment to correct alignment. When using shims to correct alignment, keep the following things in mind. First, be sure the shims you're using are as large as the feet you're putting them under. This prevents the feet from slipping off the shims. Second, use one thick shim instead of a stack of thin ones. A stack of shims often causes a springy action that could affect the alignment when the unit is operating. Also, be sure the shims you're using and the feet you're putting them under are clean and free of grease or paint. And finally, unless the bed plates of the feet are uneven, always install shims in pairs. Placing a shim under only one foot causes the motor to tilt and can throw the alignment off even farther. Well, that covers angular misalignment. Now, what about parallel misalignment? Measure for parallel misalignment by using a scale at the same 4 points, 12 o'clock, 3 o'clock, 6 o'clock, and 9 o'clock. Begin at the 12 o'clock position, laying the scale across the top of both hubs. If you find that there's a gap between the hubs and the scale, measure it with a feeler gauge to determine how far the parallel alignment is off. It will probably take you a few tries to get an accurate reading with the gauge. Just be sure to take your time so that your measurements are reliable. When you get the feeler gauge to fit snugly in the gap between the scale and the hub, take a reading on the gauge. Measuring the thickness of the gauge with a micrometer is usually faster and easier than adding up the values stamped on the blades of the gauge. Be sure to write this first measurement down before taking measurements at the other 3 points. If all 4 measurements are 0, the parallel alignment is correct. But what if all 4 measurements are not 0? Let's say the measurements at 3 o'clock and 9 o'clock are not zero. What we have then is horizontal parallel misalignment. To correct horizontal parallel misalignment, unbolt the motor from its bed plate and move it sideways until the shafts line up properly. Then measure again to ensure that everything is aligned. If the problem is vertical parallel misalignment, unbolt the motor from its bed plate and insert or remove same size shims under all 4 feet. This will adjust the height of the shaft without changing the angular alignment. Add 4 shims if the motor has to be raised. If the motor needs lowering, remove 4 shims or replace the shims that are already there with thinner shims. This brings us to a basic alignment principle. When you correct any misalignment in the vertical direction, use shims. When correcting horizontal misalignment, loosen the motor from its bed plate and shift it to the right or left. The methods we just saw work most of the time, but they're not as accurate as they could be. Also, sometimes the edges of the hubs are worn or damaged, which makes measuring at all 4 points pretty difficult. You can get around these problems by using 2 dial indicators. Dial indicators are very accurate if used properly. Also, they can make accurate measurements even if the coupling is damaged. Because of this, using a pair of dial indicators is the preferred method for measuring alignment. To use dial indicators, brackets must first be attached to the shaft. The brackets should be opposite one another, and they should be far enough apart to allow the dial indicators to fit between them. The dial indicators themselves are mounted on rods, which in turn are attached to the bracket on the motor end. What are the indicators measuring? Well, the A indicator is measuring the movement of this L-shaped bracket as it moves back and forth. Any movement in either direction would be a result of angular misalignment. The P indicator measures the movement of the L-shaped indicator as it moves up and down. Any movement in this direction would be the result of parallel misalignment. In the next segment, we'll look at dial indicators more closely and use them to measure misalignment in this system. But before we go on, let's take a short break. Now that we've covered the basic information you need to do a shaft alignment, we're going to apply this knowledge to an actual alignment job. In the last segment, we saw how dial indicators are positioned on the shaft. In this segment, we'll go through the step-by-step method for using these indicators on the job. Since it's much easier to shift the motor around than it is to move a pump with all its piping, we'll be adjusting the alignment of the motor shaft to match the alignment of the pump shaft. When the alignment is complete, we'll reassemble the coupling and do a final alignment check to be sure the job was done right. Before positioning the dial indicators, all dirt and paint is cleaned from the places where the clamps attach to the shafts. This ensures that the clamps get a good, secure grip on the shafts. We also check the shafts for burrs or ridges that could cause the clamps to rock. Burrs or ridges can be removed with a small, fine-toothed file. Dents or keyways won't interfere because the clamps can be attached to bridge these spots. If there are oil reservoirs that have been drained, squirt some oil into the top of each bearing. Then rotate each shaft to spread the oil around the entire bearing. Before mounting the dial indicators, install the grid on the hubs. This is important because it ensures that the hubs will rotate together. It's best if the grid isn't forced too tightly into the hub teeth. Otherwise, it could put stress on the hubs and affect your measurements. Next, attach the dial indicator brackets to the shafts. Leave a little room between the bracket and the hub on either side. Make sure that each bracket is securely attached, but don't tighten them so much that you put gouges or other marks on the shaft. Now you can attach the clamp and rod to the top of the upright bracket on the motor shaft. Be sure the rod runs parallel to the crosspiece of the opposite bracket. Slide the first dial indicator onto the rod. This dial indicator measures angular alignment. It should be positioned so that its stem presses against the butt end of the L-shaped bracket. In this position, it will be able to measure any change in distance between the two brackets. The second indicator measures parallel misalignment. It should be mounted so that its stem presses against the top of the bracket crosspiece. We're first going to measure for vertical angular and vertical parallel misalignment. But before we do, we have to cancel out all readings of possible horizontal misalignment, so they don't throw off the vertical readings. Begin by rotating both shafts until the dial indicators are in the 3 o'clock position. Then, reset both indicators to 0. Zeroing the indicators gives you a reliable starting point for the next step. Rotate both shafts 1/2 turn so that the dial indicators end up in the 9 o'clock position. When the indicators are at 9 o'clock, take an accurate reading from both of them. The next step is critical. Write down how far away from 0 each indicator needle has moved, and divide each amount by 2. By dividing these measurements in half, you'll determine how much each indicator must be adjusted in order to cancel out readings of horizontal misalignment. With the indicators still in the 9 o'clock position, reset each one by the amount you have calculated, halfway between 0 and its 9 o'clock reading. Then, rotate the shafts until the dial indicators are at 12 o'clock. The readings that now show on the indicators should be accurate measurements of vertical misalignment. Be accurate when writing down these measurements. This involves both reading the indicators correctly and knowing which indicator measures what. The parallel indicator will tell you how much the motor shaft has to be raised or lowered to restore parallel alignment. A plus reading on this indicator means that the motor shaft hub is too low and must be raised. A minus reading means that the motor shaft is too high and must be lowered. The reading on the indicator tells you in thousandths of an inch or in millimeters exactly how much adjustment is necessary. The motor shaft is raised or lowered by inserting or removing the proper sized shims. The angular indicator measures angular misalignment. If in the 12 o'clock position it gives a plus reading, the gap between the tops of the hubs is too narrow. If you get a minus reading, the gap at the top is too wide. Unlike the reading on the parallel indicator, however, the reading on the angular indicator does not tell you how much adjustment is necessary. This is because the reading is affected by how far the indicator is from the center line of the shaft. In this example, the gap at point A is wider than the gap between the hubs. If longer brackets are used, the distance at point A increases, even though the gap between the hubs does not change. In either case, what you have to do is find out how much adjustment is necessary to put the coupling back into angular alignment. The formula for figuring out the amount of adjustment using readings on the dial indicator is in your text. After you read the section, your instructor will answer any questions you might have. Once you figure out how much vertical adjustment must be made to the shaft, make a sketch of the motor, shaft, and coupling. In your sketch, show the location, number, and size of the shims you have to add or remove to correct the vertical misalignment. Then, use the sketch to make the actual adjustments before you begin to measure horizontal misalignment. When you have measured and corrected both the vertical angular and vertical parallel misalignment, measure one more time to be sure the alignment is correct. With the final check on vertical alignment completed, you can start on both types of horizontal misalignment. Earlier, we canceled out all horizontal misalignment so that we could measure the vertical alignment accurately. Do the vertical readings have to be canceled out to measure the horizontal alignment? No, because the vertical misalignment has already been corrected. There is no vertical misalignment left to affect our readings. By zeroing the indicators and rotating them into either the 3 o'clock or the 9 o'clock position, you get an accurate reading of horizontal misalignment. Since horizontal misalignment is corrected by shifting the motor on its bed plate, loosen the bolts from the motor feet. In this case, the mechanic is correcting horizontal parallel misalignment. He does this by tapping both ends of the motor so that it moves sideways. Both ends of the motor should be shifted the exact same distance, otherwise the angular alignment will be thrown off. He keeps his eye on the dial indicator that measures parallel misalignment because he knows that when the reading reaches 0, the alignment will be correct. Of course, as a final check, he'll have to measure again to be sure the problem has been corrected. When you've checked the shaft alignment and you're satisfied that it's correct, disassemble the measuring equipment. Remember, you're dealing with sensitive instruments. They should be handled with care and cleaned after each use. The coupling is now ready to be reassembled and put back in service. When the equipment is back together and ready to go, give it an operating test. During the test, be on the lookout for telltale signs of misalignment, vibration, high bearing temperature, and unusual noise. What we've seen here is one correct method for performing a coupling alignment. There are other methods that you'll learn about from other maintenance mechanics and through your own experience. Just remember that if you're faced with an alignment job you're not sure how to handle, check the manufacturer's instruction manual to find out what to do. With the proper procedures and a basic understanding of alignment principles, you'll be on the right road toward keeping the equipment in good order and working at peak performance.